This is an example of an AC node solutions problem in Circuit Tutor on the hard level, or level 3. Now, as always, we have examples available at multiple levels of difficulty, so it might be a good idea to view some of those prior to starting the exercise. Here I'm going to go straight into an exercise as illustration. So our first task, as always, when doing nodal analysis, is to pick a reference node. If we fail to do that, then we will have no way to compute any nodal voltage because there will be no absolute values established for them. So generally we want to pick a node that has as many things as possible attached to it, including, if possible, voltage sources. So this would have 2, here we have 3, 3, 2, and 2. So the one that has the most and also has a voltage source would be this upper middle node. So that would be the preferred place to put the ground or the reference node. So I'll do it there. That will minimize the complexity of the equations that we have to work with and will therefore simplify the algebra. Now, being a solution game, we have been given the KCL equations for the circuit, so we did not have to write those. We do, however, have to write the voltage constraint equations for each of the two voltage sources in this circuit, being a nodal analysis, and then we have to write a sought variable equation for the sought current, which in this case goes through a voltage source. So let's do that. The voltage constraint equations, we'll select that type of equation. And so let's do it first for the V2S source here. And we notice that that's connected between two different nodes, neither of which is the reference node. So we will need the difference of two node voltages there. And that will be equal to a fixed value since this is an independent source. So we have V3 on the positive side and V1 on the negative side. So that will be V3, therefore minus V1. Again, positive side, negative side. And then the value of V2S, which we read off down here, is 4 angle 30 degrees. So we'll just enter that. And then we'll check that equation. And that is correct. Then we'll enter another voltage constraint equation for V1S, which is connected between a node and a ground node. So that will require one node voltage equal to a particular value. And the positive side here is node 4, so we have V4. And effectively that's V4 minus 0, since the reference node, of course, is at a voltage of 0 volts. And then the value V1S we read off here as 1 angle 0 degrees. So we'll enter that. And so that equation is correct also. Next, we have to do a sought variable equation for a sought branch current that goes through a single circuit element. So we'll select sought branch current from the menu. And then we have I naught equal to. And now, being the current of a voltage source, we cannot find that directly because remember that the current through a voltage source is whatever it needs to be in a circuit. And that's determined by the rest of the circuit, not by the source. The source only fixes its voltage, not its current, because it is a voltage source. However, in this case, we see this voltage source is actually in series with two different elements, a capacitor and a resistor, and so we can simply use one of those elements to determine the current instead. So for example, I could write this as V1 minus V2 divided by 5 ohms. So again, I'm choosing a sign convention such that V1 minus V2 with a positive sign, that corresponds to a current going into the positive side, the V1 side, and therefore that will be in the same direction as the defined direction of I naught. So that would be consistent, and again, as always, everything in circuits we have to be careful about the signs and the polarity, but this will be appropriate here, provided that we have V1 minus V2. So let's check that equation, and that is correct. And again, we could have alternatively written that as negative V3 divided by minus J4 ohms, which might have been a little bit simpler, I guess, but either way we can still compute what it is. Okay, so now we've written all the required equations to solve this circuit, and so we'll just click no more equations. And now the next step in a solution game is to basically prepare to solve these equations for the desired sought variable. And intermediate to that, of course, we are going to have to find the node voltages V1 and V2. So to do that, we need to put the coefficients of all but the sought variable equations, namely the voltage constraint and KCL equations in this case, because there is no dependent source, into standardized form, which means we have a single term involving each variable on the left, and then we put all constants on the right-hand side of the equation. In doing that, we are allowed to multiply each equation by a constant if you wish to do that. For example, here you could multiply through, for example, by 20 to clear at least the real part of the fraction. Now you still have a minus j, but that can be brought upstairs as a plus j, using the fact that 1 over minus j is j. So that might simplify the equations. We could do that. And you could do a similar thing down here. You cannot, however, add this equation to this one or plug this equation into down here or anything of that nature. So we could not replace, for example, V4 down here by the 1 value. That's not permitted in writing these equations. We will do that in the next step where we solve the equations, however. Okay, so let's put those equations in. Our first equation says V3 minus V1 equals 4 angle 30 degrees. So V3 will have a coefficient of 1, and V1 will have a coefficient of minus 1. And then we'll have the 4 angle 30 degrees on the right-hand side. Notice that all of these must be entered over here on the right-hand side in polar form, whereas these numbers must be entered in rectangular form. Remember, in general, these are going to be complex numbers, but the single text box indicates that we need to use rectangular form, as it indicates here in the instructions. Okay, so the second equation says that simply that V4 equals 1 angle 0. So that'll give V4 a coefficient of 1. All the others, of course, will have coefficients of 0. And then we just put a 1 here, and then the angle 0. And that does the second equation. For the third equation, we see that V1 has a coefficient of 1/5 or 0.2. So we'll put 0.2. And then V2 in this equation has a coefficient of negative 1/5, which would be negative 0.2. And V3 has a coefficient of 1 over negative j4. And remember that when we're taking the reciprocal, we must take the reciprocal of everything in the denominator, not just of one of those items, which sometimes people make a mistake and somehow put the 4 up on top, which would not be correct because the 4 is in the denominator, not the numerator. So 1/4 is simply 0.25, and 1 over negative j, we may recall, is just j, because remember j squared is always equal to negative 1 by definition. So therefore 1 over negative j is j. So we can say that the top coefficient is j times 0.25, not j4. Okay, so that would be the coefficient of V3. So we'll put j 0.25. And that does it for this equation. The right-hand side is 0. There are no constants here. And then for the next equation, we look at the V1 term, and that just has a coefficient of negative 1/5 or negative 0.2. For V2, we have a coefficient of 0.2, 1/5 that is, and then this term is going to be imaginary. So I'll just start out with the real part, which is the 0.2. And then for the imaginary part, again, this is 1 over j4, so similar to what we had here, but this time 1 over j is going to be negative j, for the same reason that 1 over negative j is j. So we're going to have negative j 0.25 for the imaginary part, which adds, of course, to this other term. So we're going to write minus j 0.25. And that'll be the complete coefficient of V2. Just those two terms, of course, add together. Okay, there is no V3 here, so that has a coefficient of 0, and V4 will have a coefficient of negative 1 over j4, and that would correspond to negative 1 divided by j would be j, because j squared is negative 1. So that will be j 0.25. And finally, the constant term here gets added to both sides of the equation. So on the right-hand side, that becomes simply 7 angle negative 45 degrees. So that should complete all the equations, and now we'll check those. And those are correct. Now the next step would be, and of course those simplified equations now have been written here on the screen for us. So the next step will be to form those into a matrix equation, or cast them as a matrix equation. And that's very easy to do in the program. You just click the button that copies those from the simplified equations so that we don't have to retype all of those coefficients. It's not necessary to do that unless you feel like doing it, I guess. And remember that each one of these rows of the matrix equation corresponds to one of the original simplified equations. So for example, here it would be negative 1v1 plus 0v2 plus 1v3 plus 0v4 equals 4 angle 30. And that would be the first equation here. And then, for example, the last one would be negative 0.2 times v1, and this coefficient times v2, 0 times v3, and j 0.25 times v4 equals this constant. And again, that's the same as this equation. And of course, you can do that for the other two rows as well. So that should all be correct. And now the matrix equation is written there if we need that. We probably won't really want to use matrix methods, however. I think generally, because we really only have two complicated equations, namely the KCL equations, and these other two are really quite simple in form, and they lend themselves to substituting directly into these other equations. So I'm going to use elementary algebra methods to do that rather than any kind of Gaussian elimination. I mean, you can do that if you wish, but I think that the direct substitution is really probably an easier method in this case. The full matrix methods are really only needed if you had more than two KCL equations, for example. Okay, and your instructor might ask you to turn in the written algebra that you did for this. If so, then you should retain that and turn it in if they've requested that. Otherwise, it's a good idea to keep that just as your own record of what you've done, so you can refer to it later when you're studying in case you need to review how to do the complex algebra. Okay, so our goal now is to find those four voltages. And keep in mind that we can, if for some reason we prefer to go right to the last step, we could skip this step and just enter the value of the stock current directly. That will be accepted as long as you get it right. But I'm going to go back and do the node voltages first just so that I can check that they're correct before I do the last step. I just feel that that may be a little bit easier. Okay, so let's go and do the algebra now on paper. So I'm going to make this visible over here. And so here are simplified equations, and again I'm going to start with the two more complicated ones, which were these KCL equations, which are the lower two equations here. And I simply copied those over. So we have the 0.2v1 minus 0.2v2 plus j 0.25v3 equals 0. That's the first one here. And then the second one, the negative 0.2v1 plus this coefficient v2, etc. And that's just the second equation that we have the bottom row basically here. So then I've also copied over the constraint equations, which just say, for example, v3 minus v1 is 4 angle 30, and v4, 1 angle 0. For our purposes, we can just call that 1 because it's the same thing in rectangular format at least. And so that obviously will be substituted in directly for this. And then we want to substitute here, and so we'll just solve this for v1, for example. So just subtracting here from both sides, we can have v1 is equal to v3 minus 4 angle 30 degrees. And that can be substituted into here as well. And when we do that, we're going to have only two equations in two remaining unknowns because we will have eliminated v1 and we will have eliminated v4. Again, notice I put bars here. That's just to indicate they're complex numbers, but I guess that's optional. Okay, so now I'm going to take this first equation and do the substitutions. So the 0.2 now multiplies the v1, but I'm going to use this expression here, the v3 minus 4 angle 30 for v1, minus 0.2 v2 bar plus j 0.25 v3 bar as originally indicated, and there's no v4 there. So that's that equation. And then now I want to simplify that since I now have multiple terms, for example, in v3. I'm going to combine those terms. So first of all, I'll just write it in proper order with the negative 0.2 v2 bar first. And then for the v3 bar, you see that we have 0.2 plus j 0.25 is the coefficient of the v3 bar, combining those two terms. And then we also have a constant term here, which is going to be now basically multiplying that in our head, because 0.2 has an angle of 0, obviously being a real number. That just becomes 0.8 angle 30 degrees. Now again, we are adding 0 degrees in principle to 30 degrees, so that won't change the angle because this has an angle of 0. And then the 0.8 angle 30 degrees, we added that to both sides to bring it over here and put it on the right-hand side. So we put that in a little bit more standard form now. And then we'll take this second equation here, which was again one of the KCL equations, and now do similar substitutions. So following the dashed line down here, we have negative 0.2 times that V1 expression, which was over here, the V3 bar minus 4 angle 30 degrees, plus then the 0.2 minus J 0.25 V2 bar that we had here, and then the V4 bar, I'm going to plug that in as just 1, and then because that now becomes a constant, I'll subtract that from the right-hand side. So I have the original right-hand side, which is the 7 angle negative 45 degrees, minus J 0.25. So when V4 bar is 1, that just becomes the minus J 0.25 on this side. And once again, I want to simplify this equation. So I'm going to bring the V2 bar term first, since that's the first variable, should be on the left. So I just move that one over here. And then V3 bar, now we see that we have negative 0.2 V3 bar. And then this term basically becomes a constant multiplied times this. And so I can just do that multiplication in my head, because 0.2, again, that's really 0.2 angle 0 degrees. So multiplying that, that just becomes 0.8 angle 30 degrees. And then I'm going to add that onto both sides, getting rid of this negative sign, therefore. And so that, no, I'm sorry, that because there's 2 minus signs, that actually becomes a plus sign. So I'll subtract that from both sides, is what I meant to say. And that becomes the minus 0.8 angle 30 degrees over here, adding to what I originally had up here. And then I'll rewrite that and then basically so that becomes this, and then rewriting that we have the 0.2, well, the same term here, minus 0.2 V3 bar, and then I simply evaluated this expression. So I did that on the calculator, adding those 3 numbers together. I suppose I can illustrate that step here. So I'll use a TI-84 Plus emulator here, just to illustrate the simple process. And we want our number, well, actually it doesn't really matter what format our number is in here, but I'll have it come out in polar form. So notice that I am in the polar mode. For sure you don't want to be in a real mode there. I mean, you could choose rectangular in this case if you like, but it won't really matter. But I've just chosen polar mode here. If you're not in the correct mode, you'd always have to go into the mode and go down here and select either rectangular or polar mode. You certainly cannot use the real mode, because that would not work for complex numbers. I've also chosen degree mode because I'm going to have angles. I want them to be in degrees, because those are the units of angle used in Circuit Tutor and that are really typically used by engineers. Okay, so we're in the correct mode already, and we'll just enter those 3 numbers to subtract. So we have 7. Now, I've pre-programmed, as I usually do, a variable e, which will contain basically, so I put 7 and I'll put e. And that e is a pre-programmed value, which is just little e, the base of the Neperian logs, to the power I, pi, divided by 180. And that's because this calculator has a quirk that all the arguments of complex exponentials must always be in radians, even when you're in degree mode, which is a little strange, but that's the way this calculator works. So we have to deal with that. On a TI-89, for example, that would not be the case, but in this calculator it is. So now I need to raise that to the angle, which would be the negative 45. And then exit that, and then subtract the, instead of j here we put I, which is the second decimal point here, 0.25, and then subtract the 0.8, and that's angle 30. So again, I'll use that e key, that e variable rather, to the 30 degrees. And that should be the complete expression. So I'll just enter that, and that gives me the value, which as I've written here is 7.034 negative 52.76 degrees, rounding to 4 digits. I want to carry through typically at least 4 digits in all these numbers to ensure that I minimize any round off error. Now, so I have this equation, and never mind this part right now. And then I have this other equation that I'm just copying down from here, the simplified second equation. So I have these two equations, and I want to solve those simultaneously for V2 bar and V3 bar to complete the problem. So there's various ways we could do that. We could solve the first equation for V2 bar, just adding this to both sides, for example, and dividing by the coefficient of V2 bar, and then plug that into here. And then that would allow us to solve for V3 bar. So it would express V2 bar in terms of V3 bar, give us a single equation and a single unknown. And again, algebra with complex numbers is done exactly the same way you would do it if you were dealing with real coefficients. There's really no difference, except we have to do complex arithmetic. And of course, we could have solved for V3 bar, plug that in here, or we could have solved this for either variable and plugged it in here. Plugged it in here, I mean. In any case, there's a variety of methods. So what I'm going to do is take this first equation, and I'm going to multiply it by 0.2, which is the absolute value of that, divided by this coefficient. So in doing that, I'm going to make the coefficient of V2 bar in this equation become 0.2. Then if I add it to this equation, 0.2 V2 minus 0.2 V2, of course, will cancel out, getting rid of the V2 bar terms, and I'll have nothing but V3. And so that's what I'm going to do. And of course, I have to also multiply all the terms in the equation by the same constant as per the standard laws of algebra. So this one, we already know that term's going to be 0, so I don't need anything here. So for V3 bar, I have the negative 0.2 times 0.2, which would be negative 0.04, which I can do in my head, divided by this denominator, 0.2 minus j, 0.25. And then that's going to be times V3 bar, but I factored that out here. And okay, so we have that. And then from the second part, we have just this term here. So we adding that, so we have the 0.2 plus j 0.25, which is this part of the term from the second equation, having already included this term here. So that's all the coefficients of V3 bar. And then on the right-hand side, we have this constant, which we multiply times this. So again, just written there in polar form, times the 0.2 divided by that denominator. And then we have to add then the constant in the second equation, which is not multiplied by anything. So that just is written down here since I ran out of space. Okay, so now I just have to evaluate both sides of this equation. I'll just illustrate, I guess, doing one of those computations just for the sake of completeness here. So let's put in 0.2 times 7.034. And I don't really need a parenthesis here because all three things are being multiplied, so there's no parentheses required here, although sometimes if you're adding, you might need that, or in certain situations you might need that. And then we have the E, negative 52.76. Oh, I forgot the exponent there. That's not good. So I'm going to go back and put that in. So negative 52.76. And then I'll just erase the rest of that. And then that's got to be divided by this complex number here. So I need to put that in parentheses. Otherwise, of course, by standard order of operations, it wouldn't divide by the entire thing. So it has to be in parentheses there. So we're going to go 0.2 minus I, which again, I get down here off this key, times the 0.25. And then we need to close the parentheses in the denominator. And then I can just add to that the second term, which is going to be plus 0.8. And then for the angle, remember I do the e to the power 30. And that's the 0.8, 30 degrees. And I just push enter there. And that gives us the result 5.094 to 4 digits with an angle of 3.276 degrees. And that's what I've written out here. And then we do a similar way of evaluating that, which I'll skip in the interest of time. And that would give us the 0.1952 angle 51.34 degrees. And now we'll just take this number here and divide it by this number. And again, I think I can skip that probably here on the calculator. So that will give us 26.09 angle negative 48.06 degrees volts. So that's our value for V3 bar, which we can then enter in Circuit Tutor. But we also are going to need the other voltages. So to get V2 bar now, of course, we used either of these two equations. So I can simply solve one or the other of those. So let's take the second one, for example, and we'll plug in our value of V3 bar that we just computed to get V2 bar. So for example, I've written this equation. I've subtracted this part from both sides. So I've got the 0.8 angle 30 degrees minus this coefficient of V3 bar, which is 0.2 plus J 0.25, and then multiply that times now the value of V3 bar, which is this 26.09 angle negative 48.06 degrees. And then I divided both sides by the coefficient of the V2 bar in order to finish solving for V2 bar. So that's why I have a negative 0.2 in the denominator. And once again, we can just enter that expression as written into the calculator, just making sure you use parentheses as needed there. Again, I think I'll skip the evaluation of that, but basically that will give us 38.24 angle 0.58 degrees volts. A very small angle, so I didn't bother carrying out the digits. And then finally, the V1 bar, we can use this equation, V3 bar minus 4 angle 30. So again, there's our V3 bar that we already computed, this value here, minus the 4 angle 30 degrees. And once again, we just subtract those two numbers directly in the calculator. No need to put them into rectangular form since we're using the calculator's abilities. And that ends up giving us 25.56 angle negative 56.87 degrees. And of course, these are all in volts, so I've added the units. So now we just need to go back to Circuit Tutor, and we'll enter those numbers in here. So we have, well, the V4 bar is, that's just 1, or 1 angle 0. The V1 bar now is 25.56 angle negative 56.87. And the V2 bar is just that 38.24 angle 0.58 degrees. And the V3 bar, remember, was 26.09 angle negative 48.06. And I've already entered V4, so that should hopefully be correct. We'll check that. And indeed, those are sufficiently correct. And now the last step will be to use the SOT variable equation for I naught and use that to calculate that quantity. So once again, we just take our V1 bar, subtract the V2 bar, and of course putting parentheses around that, then divide by 5. So that's another simple operation on the calculator. So I'm just going to skip that in the interest of time. And that will give us a 6.523 angle negative 138.1 approximately degrees. And that's the final value for I naught bar. And that is correct. And that's been printed now here. And then the last step is to express the SOT quantity in the time domain, i.e. to do an inverse phasor transform, because this isn't, of course, an AC circuit, just being represented originally in the polar domain, but we want to go back now to the time domain. So in order to do that, we just fill in the blanks here. So remember, we're always using a cosine function. If you're doing this by hand, you just have to remember that inverse phasors always involve a cosine function. That's just how phasors are defined. And we need to look for the omega value. Well, notice it doesn't give us omega in this problem. It only gives us f. And we have to be very careful because f is in kilohertz. That's not going to be the value of omega. Remember, omega is always 2 pi f. So 2 pi times 3 kilohertz will be 6 pi kilohertz. And let's go on the calculator, I guess, to do that. So 6 times pi. I mean, we could do it approximately, probably in our heads, but let's just do it accurately. So the 6 pi, and it's kilohertz, so I'm going to go times 1,000. So that will be 18,850. Will be close enough there. And then the magnitude will be the magnitude of the phasor, which is the 6.523. And the angle will be the angle of the phasor, which is negative 138.1. And that completes that, so we'll check that. And indeed, that is correct. And if we like, we can view a detailed explanation of the KCL equations and the SOT variable equation by clicking yes there. That's optional. And it would show you exactly how you calculated the SOT variable current, and also a detailed, if you like a detailed explanation of the KCL equation, that's available here. Constraint equations are explained in general here. So that would complete this problem.